Hello students, welcome to our second lecture on graph theory in the course of networks and complex systems. In this chapter, we will discuss origin of graph theory, which is a mathematical backbone of network science. However, why do we need networks as a separate subject if there exists a graph theory? Because there are certain subtle differences that we need to understand. Hence, we will try to get hold of it why network science is not equivalent to graph theory or why networks are not equivalent to graphs. And then we will also look into some of the quantitative characteristics of networks and which borrow concepts from graph theory. And we will try to understand what these characteristics mean for real world systems exemplified on a few systems that we see in our daily life. Finally, we will try to look into the mathematical aspects, that how we can represent these graphical objects in a mathematical entity, and we will take support of metrics, and we will represent these networks in form of adjacency metrics. So let us get started that where this origin or genesis of graph theory lies. So as I mentioned, it's a mathematical scaffold between behind network science, and the root of origin of graph theory goes back in 1736 in the city of Konigsberg. Konigsberg was a thriving city in present-day Russia, and to facilitate movement of ships and trades, city decided to build 7 bridges across the river flowing through the city. So they decided to build these 7 bridges, and this construction of 7 bridges gave rise to an interesting problem. That is, can one walk across all these bridges without crossing any bridge twice? Despite many attempts, nobody was able to find such path. This problem remained unsolved until 1736, when great mathematician Leonhard Euler offered a rigorous mathematical proof that such path does not exist. How he arrived at this conclusion? So he made a use of graphical representation of this system, and what he did, he represented 4 land areas as nodes. So he said there are 4 nodes in this particular system. That is, let us say that we have D, A, B, C, and he said that these 2 land pieces are connected by an edge. And let us, for sake of completeness, let us also draw the land and a river around that. So this was first landform, and river was flowing somewhere here like this, and this is how we end up. So this is a graphical representation of city of Konigsberg, and there were 7 bridges that were built. So we will also represent these 7 bridges here, and that's it. So what he said, that let us represent these land forms in land pieces in form of nodes, and we can consider that these 2 nodes are connected if there is a bridge running between these 2 land pieces. So here between D and C you see a bridge. So what we would do, we will draw one edge or a connection or a link between D and C. Similarly, D and A, they are connected by 2 bridges, A and B are connected by 2 bridges, and B and D are connected by 2 bridges. So this gave rise to an interesting representation in form of a network where we had something like this. And he made an interesting observation. That is, if we have more than 2 nodes in a particular graph which have even which have odd degrees or odd number of connections, there does not exist any path that would meet the condition, that is, you can cross all the bridges without crossing one particular bridge twice. Why so? Because if you arrive at a node with odd degrees, that has to be either origin or the end point, because you would not be left with any option if you are encountering a node with an odd bridge. So this Euler's proof was for the first time when somebody used a graph theory to solve a real world problem. So as I mentioned, the key findings were that if a graph has more than 2 nodes with odd number of connections, there is no way to cross all the bridges without repetitions. And if a graph is connected and all nodes have odd number of connections, as you saw that you can go from any from D to C and from C to A and A to B. So we say that all the nodes are connected in one way or another, And if all nodes have odd number of connections, there has to be at least one path that would meet the initial condition that you can cross all these bridges without repetition. However, the more interesting thing than the proof of theorem itself was that sometimes it becomes much easier if these problems are represented in form of a graph or network maps, and that's what we would do throughout this particular course. Also, the existence of path does not depend how smart we are, because I'm sure as soon as we saw this puzzle, we might have started tracing our pencils on this graph. But the point here is, it is a property of a graph. Rather than being how intelligent or ingenuine you are, you would never be able to solve this particular equation or system, because graph theoretically guarantees that such path does not exist. Now, from graph to networks, there are certain commonalities in graphs. For example, Euler represented a real world system using graph theory. And when we talk about networks, we typically talk about that networks have to represent a real world entity. And choice of nodes and links between these nodes should make a real world sense. For example, let us consider an example of World Wide Web. In World Wide Web, we would have some computers or some routers which would be connected to each other through some meaningful exchange of information, or what we call as packets in data. So packets of data. So that would represent a network. However, when we represent it in form of a node without explaining what this A and B represents, that would be a graphical representation of a real world network. Now, when we talk about graph theory, we often talk about that there is something called as automorphism. That is, same object can be represented in different ways while preserving its structural properties. However, in the context of networks, as soon as we do that shuffling, that the meaning and inferences of nodes and interactions change. Hence, we have to be careful when we shuffle networks in comparison to graphs. However, there are certain commonalities between networks as well as graphs. For example, both of these networks and graphs, they have something called as nodes or vertices. In networks, we call them as nodes. In graph theory, we call these components of those systems as vertices. For example, in Euler's example, the pieces of lands were represented as vertices or nodes. And whenever we connect these nodes by some meaningful interactions, we call them as links or edges. Again, in network science, we will commonly use the word nodes and links. However, if you refer to some of the graph theory research articles or literature, you would see they typically use V versus E. So there is a subtle difference. That is all we have to keep in mind, that the difference is that the real world representation is coming into picture whenever we are talking about networks. Now the question arises, can two different networks have same underlying graphical representation? To understand it, let us look into our next example. So here I have shown three networks. One is the World Wide Web, that is where routers are interacting with each other in some meaningful way. This is called as the actor network, that is we would connect two actors by a link if they have acted in the same movie. If they have acted together in one of the movies. For example, this actor named Marlon Brando has worked with Al Pacino in the movie The Godfather. That means there is a link that exists between them. Similarly, Al Pacino has worked with Henry Silva in movie Dick Tracy, and hence you see that there is a link between them. Now, if you look at all these four networks and this third network here is the protein interaction network, which is typically used in biology, that how protein bind to substrate and how vaccines act whenever they are injected and to disintegrate the protein structure of certain microbes. But if you look at these three networks and their graphical representation, you can just represent them by some nodes 1, 2, 3, and 4 connected by the same underlying graphical structure. And that means that yes, we can indeed represent same graph, different networks with the same graph, and same mathematical tools can apply. But again, if you shuffle some of these nodes here, that may completely change the meaning. For example, you cannot swap Al Pacino with Michel Pfeiffer, because that would mean that Marlon Brando has worked directly with Michel Pfeiffer, which is of course not true in real world setting. And hence we have to be very careful when we work with networks and their shufflings. All right, so moving to our next part, there would be some terminologies that we should be familiar with when we talk about network science. That is, we would be often talking about number of nodes, or n, that how many components are there in a network. For example, in World Wide Web, how many routers are we talking about? In an ecosystem, how many species are we talking about? In protein-protein interaction networks, what are the number of proteins? In infrastructure system, how many stations or how many road edges, how many road intersections are we talking about? So the reason I'm giving these examples is that some of you may have this question: how does it apply to my field? You see that network science would serve diverse fields depending upon what you want to represent as a network. Secondly, and we will always denote this number of nodes by n. Secondly, we'll talk about number of links, which we represent by L, which indicates the number of interactions that is happening between the nodes. And these links are rarely labeled. Usually, for example, if you have a network like this and you identify these nodes by number 1, 2, 3, if you have to represent a link, you would say that there exists a link between 1 and 2, and this representation written in first order bracket is called as tuple. And we will typically use tuples to represent or describe that how many edges are present. Now this clearly says that there is an edge between 1 and 2, there is an edge between 2 and 3, and it completely describes the graph. And that also, and this information also conveys that what are the nodes that are present. If you look at the distinct members in these tuples, that would be 1, 2, and 3. So this complete description of 1, 2, 3 and these tuples is good enough to describe the graph. We will also use this word called as degree quite often, and degree basically represents what are the number of connections particular node I has. Now in this graph, node 2 has 2 interactions, hence we can say that degree of node 2 is equal to 2. Similarly, degree of node 1 is equal to 1 and degree of node 3 is also equal to 1. And as the name suggests, average degree would be what is the sum of total degrees of these nodes divided by total number of nodes that we have. So in this case, of small network of 1, 2, 3 or small graph, because here we are not representing any real world system. Again, I said that these words can be used interchangeably. So average degree of this network or of this graph would be 1 plus 2 plus 1 divided by total number of nodes, so which would be 4 by 3. And when we are talking about, and here you see that directions does not matter, because if we say that 1 is connected to 2, 2 is also connected to 1 and so on, so we would not care about the directions. However, in certain connections, in certain networks or in certain graphical representations, what we call as directed graphs or digraphs, direction of interaction matters. For example, there are two friends A, B, and A is calling to B. Now it clearly signifies that A has made a call to B and hence the direction is important. However, when we talk about exchange of information, if A has called to B and A and B are not enemies and good friends, and B picks up the phone, there would be some exchange of information which can be represented by an undirected network. But in this case, let us say that we have some direction associated, then we say that A has some out degree and we represent this as K out, and B has some in degree and we represent this by K in, and node identifier would be often written as a superscript. So with this notation, we are good to go and look into some of the mathematical aspects of these networks.